We need to also be able to graph the functions that we've been dealing with in this unit. So we're going to look at graphing the parent function, or we're going to look at graphing what we call the square root function. So its parent function is radical x. You've seen that before. The cube root function, whose parent function is cube root x, and the cubic function, whose parent function is x cubed. Parent function means the general form or the general look of the function without any shifting being done to it, without adding, subtracting, multiplying, dividing by anything. And we'll get more into the shifting in a moment. Right now, let's just look at their graphs. So as you saw in the last video, when we talk about the domain of a radical function, we have to look at what's underneath the radical. Well, in this particular function, when we have just the parent function, when I have just an x under the radical, notice my domain is going to have to be x values greater than or equal to 0. So when I look at graphing something, when I'm first graphing something and I'm unsure of what the function looks like, I can always use a table. So I can pick x values and solve for y values. So when I pick an x value of 0, I plug 0 in and I get a y value of square root of 0 is 0. When I pick an x value of 4, I get a y value of 2. I could continue doing this. Notice that the x values I'm picking are perfect squares. I could also pick an x value of 9 and get a y value of 3. If I then plot these, I can plot the point 0, 0, and I will tell you I'm not very accurate at plotting on these little graphs, so I do apologize in advance. When I plot the x value 4 and a y value of y, so 1, 2, 3, 4 up to about right here. And then finally 9 and 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 3. Notice that this is what my function is going to look like, and I can continue to pick more x values, and it's going to continue to grow and get larger. Notice I cannot pick any x values less than or equal to 0 then, so this is going to be the look of my parent function, radical x. It is my expectation that you will be able to graph that, either by just simply knowing what the function looks like, or by creating an xy table. When I look at my cubic function, we've already seen that we can take the cube root of both positive and negative numbers, so my domain for my cubic function, my possible x values, are all real numbers. If again, I look at making a table to kind of look at what this is going to look like, if I were to plug negative 8 in, the cube root of negative 8 I know is negative 2. The cube root of 0 I know is 0. And the cube root of 8 I know is 2. I could continue to pick more values, but I don't have a graph that really suits it or that's big enough for it. So I'm going to go ahead and just choose those 3. And I'm going to go ahead and plot them. So I'm going to go ahead and go back negative 8 and then down to 0, 0, and forward 8, and up 2. And I'm going to show you that the look of the cube root function looks something like this. And it continues to extend in both directions. Finally, looking at the graph of the parent function, f of x equals x cubed. Again, my domain is going to be all real numbers since I can cube anything. And I'm going to go ahead and fill in my xy table. Negative 2 cubed I know is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. Again, if I wanted to, I could pick more values, but I'm going to go ahead and plot these. And there's my plotted points. I went ahead and did that. And now I'm going to go ahead and connect those. And this is going to be the parent function of x cubed. Next thing I'm going to look at is our shifting rules, and then from there we're going to just look at applying. Remember when we looked at parabolas, we saw that y equals x minus h squared plus k was a parabola with a vertex of hk. So in other words, the graph was shifted right h units and up k units. So subtracting from the inside of a function moves it right h unit, adding to the outside of a function moves it up k units. We're going to use those same rules on these 3 new types of functions. So I'm going to go ahead and fill in my table. So if I add h on the inside and I think about what happened with my parabola, I know that that causes the graph to go left h. So let's say, for example, I have the function y equals the square root of x plus 2. Well, my parent function is the square root function. Since I'm adding 2 inside of the square root function, I would say that I'm adding 2 inside. That's going to cause my function to go left 2. So I go left 2, and then I just graph that general shape that we just came up with a moment ago. Looking at the next one, I know from based on what I looked at with a parabola, when I subtract from the inside of a function, it moves my function right h units. So if I apply this to one of my new functions, if I have y equals x minus 3 cubed, I'm going to keep the same general shape, but I'm going to go right 3 units. So I'm going to go right 1, 2, 3. And I know my cube function looks something like this, and I kind of missed my vertex, or excuse me, my point there a little bit, but it should look something like this. Same general shape, moved right 3. Again, I know I'm adding or subtracting to the inside because my minus 3 is inside of the cube. If I add to the outside instead of to the inside, based on what I saw with my parabola, I know that causes my graph to go up k units. And notice how these two look different. When I'm adding to the inside of my function, my add is underneath the radical. When I'm adding to the outside of the function, my add is outside of the radical. And this is going to take my function and I'm going to go up 2. Other than that, it's the exact same look. So notice if I know my shifting rules and I know the shape of my graph, it's very easy for me to draw these graphs in. It does not take me very long. On the next one, what happens when I subtract on the outside of the function? Well, that makes me go down k units. So again, look at the difference between these two functions. On this first one, I'm subtracting inside the function because the subtract occurs within the cube. Here, I'm subtracting outside the function because the subtract occurs outside of the cube. So I'm going to take the same general shape, but now I'm going to go down 3. But everything else remains the same. So notice on these graphs, they look the same, it's just the different shifting. What happened when we had a negative outside of our parabola? Well, didn't it flip it upside down? We call that reflecting over the x-axis. So here, I'm going to do the same thing with my negative square root function. So I'm going to take what would have been this function's here, I'm going to kind of draw it in dots, and if I reflect it over the x-axis, I get this function right here. Same general look, again reflected or flipped upside down. Remember what happened when we multiplied a parabola by a number greater than 1? It made it skinnier. We call that vertically stretching. So I'm going to go ahead and I'm going to use proper terminology here, and I'm going to say vertically. But you put in your notes what works for you. Vertically stretched by A. It is very hard to see the look of these. What I'm going to ask you to do on these two is I'm going to ask you in class or on your own if you own a graphing calculator to look at the graphs on a graphing calculator instead of me trying to draw them because you're going to get a better idea. So I'm going to go ahead and say what happens when I multiply the outside of a function by a number between 0 and 1, by a decimal. Well, that's going to vertically compress it. It gets wider. So again, put into your notes what works for you. So vertically compressed by A. Again, these two, please be sure you look at what those look like because it is very hard. With parabolas, because you have kind of both sides so you can really see it getting skinnier and wider, it's easier. With these, you're really not going to see it as much unless you look at two graphs side by side to see that difference. Last thing I want to do is I want to look at 3 examples where we incorporate multiple rules. So the first one, I'm going to go ahead and graph example 1 and 2 in the same one. Example 1 I'm going to graph in blue. And so I know that this is my radical function, so my parent function, remember, looks like this. Whoops, I didn't do a very good job of hitting that origin. Let me try that again. Looks something, I'm still not hitting it very well. Looks something like this, and I know I'm going to go, because I'm adding inside since it's under the radical, so I'm going to go left 3, and since I'm subtracting outside of the radical, I'm going to go down 2. So going left 3 and down 2, and then I'm going to go ahead and draw in my radical function. Or, yeah, yep, it is a radical function, my square root function. So I'm going to look something like this. On example 2, I'll do that one in green. Now I have a cube function. My cube function generally looks like this when referring to the parent function. But now, because of the 2 out front, it's going to vertically stretch. And I'm going to describe how that happens by talking about the y values. And then I'm also, since I'm adding to the inside, I'm going to go left 2. When we talk about vertically stretching, because like I said, it's going to be very hard to see on these graphs, I just want to talk about what's happening to our x and y values. So when our x value was -2, when I had x cubed, -2 was -8, 0 was 0, and +2 was 8. However, when I have, and I'm not taking this whole function, I just want to look at the stretching part. When I have 2x cubed, look at what happens to my y values. -2 cubed would be -8 times 2 is -16. 0 remains 0. 2 becomes +16. So I'm moving up or down at a much faster rate. So there's that vertical stretch. So it's almost like I'm taking my kind of quote-unquote normal x value from my parent function, or excuse me, y value from my parent function, and pulling it up to a higher value. So when I graph that, again, it's going to be very hard to see. I am going to go left 2. I'm not dropping up or down at all. And then I'm going to keep my general shape. And like I said, that graphing that factor out front is going to be hard to do. Finally, last example, and I do apologize, I know this video is somewhat lengthy. I'm going to write an equation for the parent function f of x equals cube root of x that's been vertically stretched by a factor of 2, so I know I need to multiply that out front. Moved up 3, I need to add that to the back, and left 4, I need to subtract 4 from the inside. So putting that all together, I'm going to get my function f of x equals a factor of 2 out front times the cube root, and I'm going to have to add to the inside. So I'm going to say x plus 4, that'll make it go left 4, and then I'm going to add to the outside to make it go up 3. So make sure you know a couple things from this video. You need to know all your shifting rules, and you also need to know the general look of all these parent functions.